In this video, we're going to be talking about volumes by slicing. So remember back in Calculus 1 when you found the area between two curves. In this section, we're going to start talking about taking that area between two curves and either extending it upward into some kind of solid where the cross sections are the same shape but not the same size, or we're going to take that area between two curves and we're going to revolve it around some axis, creating a solid. The first one we want to start with is the first type, the ones where we're going to take the area between two curves and extend it upward into solids with cross sections that are all the same shape, though they're not going to be the same size. So in order to get you some experience or just some feeling of what we're going to talk about, I'm going to switch over to the webcam and show you some examples of solids that have the bottom being determined by the area between two curves, but the cross sections are all the same shape, though not the same size. So what you need to imagine is the XY plane is here, and what we have graphed in the XY plane is essentially a parabola. So you could either make it an upward opening parabola or you can make it a downward opening parabola. But we're going to take this parabolic shape and we're going to put it on the base so that it looks like this. So in this case, it's down here, so you can still see the parabolic shape. Now let's look at the cross sections. Now what a cross section is you're slicing it like this. So the base is here, and we're slicing it in this direction. If you turn this sideways, you can see, and I'll hold it so that you can see it through the shadows and not cast on it so it's a little clearer. Do you see that these are all squares? So the cross-section shapes are all squares. The height is given by a parabola as well. So if we turn it this way, you can see them on the other side as well. So when you turn it sideways, what you see are all of these sections that are crossed across this parabolic base, but they're all squares, all right? So this is what we mean by a solid, where you've got a graph on the XY axis trapped between two other graphs, in this case a parabola, and probably the x-axis down here, and then it rises up off the plane, and the height of each thing is given by the length or side measure of a square. Okay, so this is one of our solids. Let's take a look at a different solid. This solid has a different base. So when we look at this solid is basically based on a right triangle. So you can see that you've got the right side coming down here and then going across, and of course it got too small. I couldn't make them any smaller than this. So this is basically a right triangle base. And the cross sections, when you lay it on top of the right triangle, so the right triangle is lying in the XY plane, and when you look at the cross sections, do you see that they are all, in fact, semicircles? So they're half circles. So when they rise up off the plane and you're asking, well, how high do you know how to make the semicircle? Remember that the semicircle's base is based on this right triangle that we've got going on here, and half of the width is the radius of that semicircle. So the height is given by the radius. And so we know exactly how high to come off the screen because it's going to be the height of the radius. All right? So that's how high we come off the base. I have one more example for you. This example is based on a circular base. So again, in the XY plane, what we have is a circle. So you can see this here. So we're going to turn it so that it's sitting on the XY plane. And then we're slicing it. And as we're slicing through it, notice that all of the slices are, in fact, squares. All right? So again, how do you know how high off of the plane the height of that square comes? Well, if you think about it, look at this picture right here. So you've got the square, and this is one side of each square. So half of that must be, if you're looking at it, you've got a square. So this length right here is one length of the square. When you turn it, it has to be the height of the square as well. So when you're looking at these to determine how high off the plane it comes, You're just basically looking at the diameter of the circle. That's one side of the square, and that becomes the height. And you can see that as you turn it, you do have the squares on both sides. Now, in order to continue, what we need to do is to define some terminology. We need to distinguish shapes like this from shapes that are different and that are called cylinders. So we want to distinguish these two types of shapes. So let's return to the screen and do that now. Let's talk about what a cylinder is. If the cross sections are all the same size as well as the same shape, and the solid is created by dragging that cross section across some axis perpendicular to the cross section, we call it a cylinder. Now, for most of us, a cylinder means something different. When we say cylinder, most of us think of a Coke can shape. That's really what we think of. We think of something with a circle base that extends as a tube up to another circle base. But really and truthfully, a cylinder in mathematics means take any flat two-dimensional shape, any kind of shape at all, and pull it along an axis, creating a solid. Technically, all the shapes on this next page are cylinders. Let's take a look at them and see what they look like. So here we've got, for example, a Toblerone box. Now, this is also called a prism because the sides are all parallelograms. In a mathematical sense, a prism is in fact a cylinder, but not all cylinders are prisms. Prisms have to have parallelogram sides, and this, of course, is also considered a cylinder, but the sides are not parallelograms, so it's not a prism. This, on the other hand, which is based on a pentagram base here and here, this does qualify as both a prism and as a cylinder. Why do I say that you're taking a flat two-dimensional shape and drawing it along an axis? Well, let's look at this pentagonal prism that we have here, or pentagonal cylinder. You take the pentagon side based on 5 and you pull it this way so that all the cross sections are also pentagrams of exactly the same size and exactly the same shape. Since they're both the same size and shape, this makes it a cylinder. Let's look at the Toblerone box. Basically, the Toblerone box is based on an isosceles triangle. So I know you don't think about that when you're eating the candy because it's pretty sweet, and I got to admit, I really like the dark chocolate one. So now what we're looking at is we've got this isosceles triangle, and we pull the triangle along this central axis until we reach the second base. And this creates what is known as both a prism and a cylinder in this shape. This is what we think of as a cylinder most of the time. It is a right circular cylinder. Right means that the axis along which we pull the base is perpendicular to the base, that is, at a right angle. And circular means the base is, well, a circle. So right circular cylinder means take a circle and pull it along an axis at a right angle to the base until you reach another circle of the same size and same shape. This creates a solid. Now you can take the same thing and you can cut it in half, and this is still considered a cylinder. It's not a prism though, because the sides of it are curved. They're not flat, and they're not parallelograms. To be a prism, the sides have to be flat and parallelograms. Let's look at this. These are all, of course, boxes. They're also known as rectangular parallelopipeds, which sounds really confusing, but it's a lot of fun to say. So a parallelopiped basically means that the sides are all parallelograms. So these qualify as prisms and as cylinders. Now, when you're looking at a box, any pair of the parallel sides can serve as the bases. If I let the left side or the right side be the base, then I'm pulling it along an axis going this way. And as I pull along that axis, that length along of which I pull it is called the height. Notice that the height has nothing to do with coming straight up off the page in what we would think of as the y direction. Height instead is the distance between the two bases that are the same size and same shape. However, on a box or a rectangular parallelopiped, any pair of the parallel sides can serve as the bases. So what if I let the top of the box and the bottom of the box be the bases? Well, then the height would be the distance between the two, which is the height that we're normally accustomed to seeing. That is, the height that is parallel to the y-axis when drawn normally. In this case, then, we're pulling it along an axis that would be parallel to y. On the other hand, there are two other sides. It's kind of hard to draw, and I don't think I did a very good job of drawing it in this picture. I mean for you to use the front edge and this back edge right here as the bases. So the front and the back. This is the left and the right, the top and the bottom, the front and the back. If I use the front and the back as the bases, then I'm pulling it along an axis that is going sort of into the page, if you will. And that makes the height be this distance right here. Notice that the height depends upon the distance between the two bases. So when I'm looking at this one, which is a semicircular cylinder, the height goes between the semicircle on this end and the semicircle on that end. There's no other possible choice for a base here because there are no other two sides that are the same size, same shape, and parallel to each other. These sides are curved. They're not the same size if you slice it in that direction. That makes the height be this distance here between the two semicircle bases, same size, same shape, parallel. When we look at the Toblerone box, it's the same situation. Yes, this flat edge and this flat edge are both rectangles, but they're not parallel. They are the same size, they are the same shape because it's based on an isosceles triangle, but they're not parallel. And for a cylinder, they have to be parallel. That means only this edge here where you open the sweet box and this edge here, which is, quote, the bottom of the box, the last piece of candy, those are the bases. And that makes the long edge along the Toblerone box the height. Notice that the height is the distance between the two bases. Same size, same shape, and parallel. When we look at a Coke can, or in my case, I also have a pencil container that's this shape, you can see that you have a circular base parallel to another circular base of the same size and same shape, and the height would be the distance between the two. When we look at our pentagonal cylinder or pentagonal prism right here, notice that the two sides that are the same size and the same shape and are parallel to each other are in fact the two pentagons. It is true that all 5 of these rectangular sides are the same size and same shape. If it's a regular pentagon, that means that all the angles are the same measure. But none of these rectangle sides are parallel to each other, so they cannot serve as the bases. So the base has to be the two pentagons, and that makes the height the distance between them. Let's take a look now at the webcam view again, and we'll look at some examples of real ones in the real world so you can get a better feel for what we're talking about. Let's start with the most obvious shape, the one that we normally think of when we think of a right circular cylinder, and that would be this. This is just a pencil holder, and you can see that the base of it is a circle, and the top is also a circle. They're the same size and same shape. That makes this distance the height, which since it sits like this, is what we normally think of as the height. But again, it doesn't matter which way I turn it. If I turn it this way, the distance between the two bases, this distance here, is still the height of the cylinder. Let's look at a different cylinder. This one, of course, is based on a square. So you can see right there that we have a square base, and the other end is also a square. Now this is actually a rectangular parallelopiped. So if I hold it like this, then the height would be this distance right here, where this square and this square are the base. But because it's a box or a rectangular parallelopiped, any pair of the parallel sides will serve as bases. So let's say I make the top and the bottom be the bases. They're rectangles, same size, same shape, and parallel to each other. That makes this edge right here the height, the one that connects the top and the bottom. On the other hand, I could do the front edge and I could do the back edge because they're both rectangles, same size, same shape, and parallel. If I do that, then this measure right here becomes the height because it's connecting the two bases from the front to the back. Now I've got lots of other examples to show here. This one is an isosceles triangle. It's not equilateral like the Toblerone box. The Toblerone box is both isosceles and equilateral. This one is not equilateral. Why? Because these two edges are the same size, but this one along the bottom is longer. So when I'm looking at this particular one, notice that I do have rectangles, and the rectangles here and here are the same size and the same shape, but because they're on the slanted edges here, they are not going to be the bases. The bases have to be parallel. And that means that the only ones that could be parallel are this edge and this edge. And in fact, this is actually a right isosceles triangle because those are at right angles to each other. So we have this right triangle here and another right triangle there. And that makes the distance between the two right triangles the height. Now let's look at another one. This one is an equilateral triangle, so it's isosceles, but it's also equilateral, but it's not a right triangle. And in this particular case, all three of the rectangles are the same size and same shape, unlike the last one, where the one across from the hypotenuse, that rectangle is larger than the other two rectangles, but none of the rectangles are parallel. And that's what you see here. None of these rectangles are parallel, so they can't serve as the bases. The base has to be the isosceles or equilateral triangle here and the equilateral triangle here. Same size, same shape, parallel. That makes this distance here connecting the two bases the height. Let's take a look now at another one. This one I borrowed from my makeup table. This is basically a makeup wedge sponge, all right? So it's also considered a cylinder. And when you're looking at it, you're like, well, I've got a rectangle there, and I've got a rectangle there, and those look like the same size and same shape. I'm good to go, right? Bases. No, they're not parallel to each other because of the slanted edge. They're not the bases. The bases have to be same size, same shape, yes, but also parallel. That makes this right triangle here and this right triangle here the two bases. What connects them is this distance here. So I have a right triangle here, another in the back, and this distance here becomes the height. Let's now look at another one. This, of course, is a right circular cylinder, what you're used to. Circle base, height, distance between the two. Doesn't matter if I turn it this way. Circle base, same size, same shape, parallel. Height connects the two. This one is just a larger example of the equilateral triangle one. And you can see that we've got two equilateral triangles. I got this one probably from Hobby Lobby or Michael's. It's a flower, I don't know what you call it. It's the green foamy stuff you put false flowers in. And so this distance right here becomes the height because it connects the two bases that are the same size, same shape, and parallel. We do have rectangle sides that are same size, same shape, but they're not parallel. They can't be the base. I've got one more example to show you here. I think this one is octagonal. 1, 2, 3, 4, 5, 6, 7, 8. Yes, so this one's octagonal. So there's an octagon. It is a regular octagon in that all the angles are the same, all right? And that makes all the 8 sides the same length as well. That also means that all of our rectangle sides are the same size and same shape, but none of them are parallel to each other. So that means the height is this distance here, the edge connecting the two octagons that are same size, same shape, and parallel. let's now take a look at what a pyramid would be. A pyramid is slightly different. Now, I do have one more example of a cylinder, and this one is based on a trapezoid. So let's do one more cylinder before we do pyramids. So this one right here is a trapezoid. How do you know it's a trapezoid? Two pairs of parallel sides, or rather one pair of parallel sides, and one pair of not parallel. They don't have to be slanted at the same angle. They just have to be not parallel. One pair parallel, one pair not parallel. That's a trapezoid. This one is a cylinder because I have another trapezoid on the other end, same size, same shape, and parallel to the other one. That means that when I slice it this way, all of the cross section will also be trapezoids of the same size and same shape. That's what makes it a cylinder. All the cross sections end up being the same size and same shape as the bases. And that makes this edge right here the height. Whether I turn it this way or turn it this way or it doesn't matter. The two edges that are the bases, the distance between them, that's the height. Now let's take a look at a pyramid shape. Now a normal, what you think of as a pyramid, would probably be this guy right here. All right, this is what you think of as a pyramid, and I built this out of cardboard for some of my algebra students, so you could see the height is parallel. My string has gotten longer as time goes on, and I keep pulling on it. But basically, this one has a square base, and that means that each of the sides then is an equilateral triangle. All right, but they're not parallel to each other. But I've got a problem because I don't have two sides that are the same size, same shape, and parallel. What I do have is a base that is a square and a point, which we'll call the apex, which is, if I slice parallel to the base every time, I'll still get a square, but the squares will get smaller as I slice towards the apex. That's what makes it a pyramid. It's based on the idea of a cylinder, all right? But where all the cross sections are the same size and same shape, except that in a pyramid, they're not the same size. They are the same shape. They're going to be the shape of the base, but they get smaller as we go to the apex. And we'll talk about the relationship with the volume in just a minute. Now, this one had a square base, but there are others. So here's one that also has a square base, and you can see the sides are isosceles triangles on this one, all right, where they're drawn up taller. They don't have to be equilateral. They can be isosceles. But if it has a square base, they at least are isosceles. This one is a different triangle. Triangles do not have to have square bases. This one has, I believe, an equilateral triangle base, and then it's got an isosceles triangle coming up. Now, what happens if I slice this parallel to the base is that all of the shapes look like the base, but they get smaller in size as I move towards the apex. Now, you may not normally think of this right here as being a pyramid, but in fact, it is a pyramid. Now, it's lost its tip, so you'll have to imagine it comes up to a point. But the truth of the matter is, a cone, a half cone, is in fact a pyramid. The base is a circle, and if I were to cut this and slice it parallel to the base all the way up, wouldn't I get a circle every single time? I get the same shape as the base, but they would get smaller as I went towards the apex. That's the definition of a pyramid. So it's very similar to a cylinder, but it's not exactly the same. Let's go back to the screen and let's talk about the formula and the relationship between the volumes of a cylinder, where all of the cross sections where you cut it are the same shape and the same size, and the volume of a pyramid, where when you slice it parallel to the base, you get all the same shape as the base, but smaller in size. Let's go back to the cylinders for a moment. How would we find the volume of any of these cylinders? The answer is very simple. Find the area of the base and multiply it by the height. It doesn't matter whether the base is a pentagon, an equilateral triangle, a semicircle, a circle, or a rectangle. Find the area of the base and multiply it by the height. That will give you the volume of a cylinder. Now, it is possible to have a cylinder that is what is known as oblique. That means slanted at an angle. The cross sections will still be the same size and same shape. They're just not lined up one to the next. The volume will be the same formula, but in this case, the height is no longer an edge of the solid. It is instead the perpendicular height. We're not going to be working with oblique cylinders, so you don't need to worry about those. Let's now look at the pyramid shapes. The pyramids, like the cylinders, have cross sections that are all the same shape, but instead of the two bases, they have a base, one base, and an apex, or the point at the top. The cross sections get smaller as you go from the base to the apex. Notice that this one right here is a hexagonal pyramid. That means the base is a hexagon, and as I slice it parallel to that hexagon base, all of my cross sections will also be hexagons, but they'll be smaller as I get towards the apex. This one is a right triangular pyramid, where the base is a right triangle that you can see here. As I slice parallel to the base, all my cross sections will be right triangles, but they'll get smaller as I get to the point. The volume for a pyramid is related to the volume of a cylinder with the same base and same cross sections. It's 1/3 the volume of the cylinder. I know that sounds crazy, but that's really all it is. So what do you have to do then? You need to take the area of the base, multiply by the height, and then divide by 3. That will give you the volume of the pyramid. Again, take the area of the base, multiply by the height, and divide by 3. Let's now look at the volumes of solids that aren't exactly either cylinders or pyramids, but do have the same shape cross sections. These are the ones that I showed you at the very beginning of the video. Let's look at some examples here. For this example, the base is between the curves y equal x squared minus 4 and y equal negative x squared plus 4. In other words, here's our downward opening parabola, negative x squared plus 4. You can see it's shifted up 4. And here's the one for x squared minus 4. You can see it's the normal parabola that's been shifted down 4. You can see that they create some area in between them. This is the base. In other words, this is what the shape is sitting on. When we have equilateral cross sections, equilateral triangle cross sections, what that means is rising up off the page, and here you can see in the background your downward opening parabola and your upward opening parabola on the bottom, and these equilateral triangles that are rising up off of it. Here's a side-on view that gives you the shape of the equilateral triangle a little bit better. Now, what if we had instead isosceles triangle cross sections? Would that change the shape? And the answer is yes, of course it would. These are isosceles right triangle cross sections. How do I know? Because this side is perpendicular to this side, so it's got to be a right triangle, and this side are the same length. That makes it isosceles. But this side, the hypotenuse, is longer. You can see by looking at the two shapes that they are very, very different. This one goes straight up in the air in a sense, and this one is slanted a little bit, edged towards the downward opening parabola side. That means that the volume of the two shapes is going to have to be quite different, and that's what we want to focus on. How do we find the volume of these shapes? What if instead we had one that had square cross sections? This is yet a different shape where it doesn't even come up to a point like the first two did. In this particular view, all of the cross sections are squares, and it rises up off the page, and it reaches these flat edges along the top. This is bound to have a different volume than the first two. In this particular view, we've got pentagon cross-sections. Regular pentagon, meaning the 5 sides are the same length and the 5 angles are equal to each other. This must have a different volume than all the previous 3. We have one more example to look at, and that's a semicircle cross-section. This is where we still have the downward opening parabola for the top of the base shape and the upward opening parabola on the bottom of the base shape. However, rising off the page, we have half circles or semicircles. This is going to have a different volume than all the rest. There is no known formula to give you the volume of all of these shapes, but we can compute it using a definite integral. That's what we need to focus on now. So how do we find the volume of these shapes that all have the same base, which is the area between the 2 parabolas, but that have different shape cross-sections and come up to totally different heights and have a totally different appearance? We do this by slicing the solid into pieces. We estimate the volume of each piece, and then we add the volumes together. All the slices need to be parallel to one another, and when we put the slices back together, we should get the whole solid. Remember the visual image of the shapes I showed you at the very beginning of this video. Those were pieces put together with foam board. That's what we have. We have a bunch of different slices, and each individual slice, we're going to find the volume of it, add the volumes together, and approximate. Of course, this sounds like a Riemann sum because it is a Riemann sum. Now, which direction to slice it in is actually very important in the computation. Some directions are easy, and some are extremely difficult or even impossible. You need to slice it so that the cross sections all have the same shape. By that, I mean, looking at the picture, all the cross sections are like semicircles, or all pentagons, or all the cross sections are squares, or they're all isosceles right triangles, or they're all equilateral triangles. In other words, all the cross sections need to be some geometric shape that you recognize from geometry. They need to be something for which we can find the area. That means you need to use a formula from geometry whose area you know or can look up. We will also try to make our slices be parallel to the x-axis or the y-axis. All of your homework problems and web work had better be slicing parallel to the x-axis or the y-axis. If not, you need to let me know, but I can't imagine that there are any in there that are slicing at a different angle. We're then going to compute the area of the cross-section by using a geometric formula for the area of a square or the area of a triangle or the area of a semicircle, and then we're going to compute the definite integral. To get the volume of each slice, we'll treat each slice as if it were a cylinder. Now, what do we mean by treat each slice as if it were a cylinder? Let's take a look at this picture right here, where we have an not equilateral, but an isosceles right triangle. When we're looking at this right here, I mean take off this one triangle and think of that one single triangle as if it were a cylinder. How does it become a cylinder? Well, you have 2 sides that are isosceles right triangles, the one here in the front and the one at the back. They have an edge connecting them, which is this edge right here. It becomes this edge right here when you turn it sideways. Yes, that looks like the change in the x value, and in fact it is. That change in the x value is the, quote, height of the cylinder. Let's take a look at a different one. How about our squares? Squares are easier to think about than pentagons. Let's pull off this square right here, the second one in when you're looking at it from the right. If I pull this off, do you see that I've got a square on the front and I've got another square on the back, same size, same shape? I'm going to let the square in the front and the square in the back be the bases. This tiny little edge right here, this very thin thickness, then becomes the height of that cylinder. This particular square right here is a different cylinder, and this tiny little measure right here going back and forth is the height of that one. That's what we're going to do. We're going to treat each slice as if it were an individual cylinder. We're going to compute the volume of that cylinder, and then we're going to add them all together. In this way, we can estimate the volume of the solid. We'll treat it as a Riemann sum, and we'll take the limit as the width of each slice goes to 0. Since the width of each slice is also the height of the cylinder, this is as the height of the cylinder goes to 0. Note that the height of the cylinder is not at all what we mean by the height of the shape. I've got a height of the cylinder connecting the two bases, but it also has a height coming off the page or off of the XY plane. Those are not the same height, so don't confuse the two. Now let's take a look at this next example. In this particular picture, we have an isosceles right triangle. You can see the right triangles right here. This is the right angle right here. There is a height for the equilateral triangle, which does not compute and does not count as the height of the cylinder. Each individual slice is its own cylinder. Each side that is an equilateral triangle is the base, and this width of the slice becomes the height of that cylinder. We have two heights, height coming off of the plane and the height of the cylinder. They're not the same. In our case, the height of the cylinder is this little dx measure, and yes, it looks like the differential because it is the differential. The height of the equilateral triangle is going to be the height of the shape in order to find the area of the base. Remember that our formula for the area of a cylinder is area of the base times the height of the cylinder. The height of our cylinder is the differential dx, so I need to find the area of the of the isosceles right triangle. I keep saying the wrong thing. So now what we have is the area of the triangle, which is 1/2 the base height of the triangle, not height of the cylinder, and that will give me this value right here. So I'll take area of the base, 1/2 b times h, multiply it by the height of the cylinder, which is the differential dx. Now, on the next picture, what we're going to do is we also need to figure out what is going to be the base and the height. How do we find the base and the height? This is an isosceles right triangle, which means that the base and the height have to be the same measure. Remember, in an isosceles triangle, two sides are the same length, and that would be the base and the height, since the hypotenuse of a right triangle must be longer than the legs. So the height and the base are the same. But what are they? Remember that the base is also this edge here, and the base is sandwiched between the downward opening parabola and the upward opening parabola. So the length of the base, which is also the length of the height of the right triangle, must be the distance between the downward opening parabola and the upward opening parabola. That means that the base is f of x minus g of x. And that's also the height because it's an isosceles triangle. So the area of the triangle is 1/2 of f of x minus g of x. This is the base, times the height of the triangle, which is f of x minus g of x, again, since it's isosceles. This gives us 1/2 f of x minus g of x squared. This means the volume of one slice is the area of the triangle times the differential delta x. Remember that delta x is, in fact, the height of our cylinder. This delta x right here is the height of the cylinder. That's the distance between the two bases that are the same size, same shape, and parallel. So the area of the triangle, area of the base, times the height of the cylinder, gives us the volume of the cylinder. This is the volume of just one single slice. Just one, not the others, just one. Then to plug in the rest of the formula for the area of the triangle, we have 1/2 the quantity f of x minus g of x quantity squared times delta x. Now, we add the volumes of all the individual slices together, which of course is a Riemann sum, and we take the limit as the number of slices goes to infinity, which means each individual slice's thickness is approaching 0. That tells us that we have a definite integral. If we're going to be slicing along the x-axis, that means that we go from the leftmost slice's x-coordinate to the rightmost slice's x-coordinate, and the area of the particular cross-section multiplied by the differential dx gives us the integrand. This gives us the definite integral from a to b of the area function times the differential dx. Remember, the dx represents the height of the cylinder, and a of x represents the area of the cross-section. If we're slicing along the y-axis, then what we're going to have is the volume goes from the bottommost slice's y-coordinate to the topmost slice's y-coordinate. And then we'll have an area function in terms of the variable y, and the differential will be dy. Most of the time, ours will be along the x-axis. When we're looking at the shape up here, that is the way we cut it. If you look at the picture and you turn it this way, you can see that I sliced it so that the differentials are all dx. How do I know the differentials are dx? Look for the narrow end of these boxes. The narrow end of the box is always the differential dx. This is a long side, and that makes this the differential dx. If I were to draw the rectangles so that they were running horizontally, then the short side would be along the y, and that would be a differential of dy. All of the pictures that we have up here are sliced along the x-axis. That means that when we make the cuts, the differential is dx. Even though we're slicing parallel to the y-axis, it means we're slicing along the x-axis. Let's now look at the next piece. Let's look at this Geogebra Applet that will help you to see these solids. This is a hot link. You can click on it now to go to solids form from certain cross sections. We're going to take that to look at this next example in example 1. Example 1 says, let R be the region in quadrant 1 bounded by the coordinate axes and the curve 1 minus x squared. 1 minus x squared is a downward opening parabola shifted up 1. In other words, it looks like this. To restrict it to quadrant 1 means we cut off the part of the parabola that falls in quadrant 2. It's also bounded by the coordinate axes, which we mean the y-axis and the x-axis. So we're going from x equals 0 to x equal 1. Suppose a solid has this as its bottom and the cross sections are perpendicular to the xy plane and parallel to the y-axis are squares. In other words, if I turn it sideways, I can see that these are all square shapes. And so it's rising off of the plane as a bunch of squares coming up. The distance of the square, the lengths of the sides, are given by the height of the parabola 1 minus x squared and its distance from there to the x-axis. So the length of each side is basically the y value on the parabola. This is going from y equals 0, which is the x-axis, up to 1 minus x squared. Let's take a look at what it looks like inside this Geogebra Applet. This one is a pretty small region, so it's a little bit hard to see it on the Geogebra Applet, but I'll help you to see how to find it. When you click on the link, it will take you to a page that looks like this. You know it's Geogebra because that will appear in the upper corner. When you're scrolling down, you'll get this shape as the beginning shape for all of them. This is not the shape that we want. We want to focus on this region right here in quadrant 1. We want our cross sections to be squares, so we're going to click on squares. Our upper function is going to be that downward opening parabola 1 minus x squared. Yes, you can use the caret symbol to get the square. Now, the bottom of our shape is the x-axis, which is the equation y equals 0. Notice that it still doesn't look anything like what it should. That's because I'm going from the wrong x-coordinate to the wrong x-coordinate. Let's look back at our picture again to make sure what we're supposed to be looking like. In our picture, what we have is going from x equal 0 to x equal 1. This is where the parabola intersects the x-axis. This is where it intersects both the x and the y-axis at the origin. So we want A to be x equals 0 and B to be x equal 1. Come down here, you can either click or you can use the slider bar. I prefer to highlight and change, and that way I get exactly what I want. Now I've got it going from 0 to 1. Notice that my picture is so tiny I can't see anything. Let's change the number of boxes. Let's see if we can change the number of boxes to maybe 6. Enter 6 and then hit return. Now go on top of the picture, put your cursor here, and scroll so that the picture gets bigger and bigger. Do you see how it's getting bigger and bigger? Make sure that when you scroll that you have your cursor directly over the shape. It's going to focus on wherever your cursor is. So if you have the cursor over here, it's going to focus here and you're going to lose your picture off in the corner. So make sure you have it on the shape and scroll. Notice that I can change to having more boxes and more boxes by pulling the slider bar. Do you see that as you get more boxes, you get a more, how can I put it? A better image of what the solid looks like. You can also take this and rotate it so that you can see the top and the bottom. There is the base right there. There's my downward opening parabola intersecting the x-axis at x equals 0 and x equal 1, and the y-axis at y equal 1. When I rotate it this way, I can see that I've got all squares for my cross sections coming off the page, and my slices are made parallel to the y-axis, but that makes the narrow end, the differential, if you will, be dx. Remember that the dx is the short end of the shape, and that's this end here. If we turn it this way, you can see that the strips are longer in this direction and shorter in this direction. That makes the short end the differential, which is dx. If they were turned this way, then the differential would be dy. What we need to do is take each square and compute the volume of each square and then add them all up as a Riemann sum. This is what we're trying to do. Let's return to our page and start doing the calculations. Notice that the height of each square-based cylinder is the differential dx. That's this small measure here between this right edge, which is the base, and the left edge, which is the base. These are rectangular parallelopipeds, which we could technically use any pair of the parallel sides as bases. But to make it easy to compute, we've sliced parallel to the y, and that makes the differential dx. That means that the left side and the right side of the boxes become the bases, and the distance between the two bases is the differential dx, and that's the height. What will the length of the sides of each square be? Well, since the squares have to fit between the parabola and the x-axis, that means that the length of each side of each individual cylindrical square is the distance between 1 minus x squared and y equals 0. So the area of each square would be 1 minus x squared minus 0 quantity squared. In other words, 1 minus x squared quantity squared. Now we want to set up our integral so that we can solve it. Remember that the formula for the integration is the integral from A to B of the area of each cross-section times the differential, which is the height of each cylinder. Our cross-sections are squares. We're going from x equal to 0 to x equal to 1. That will be our limits of integration. So we're going from x equals 0 to x equal 1, and now we need our area formula for each base of the cylinder, which is 1 minus x squared squared, since the area of a square is side squared. Now we multiply by the differential dx, which is the height of each cylinder. That's it. That's the hard part. The hard part is getting the integral written down, and computing the integral is the easy part. Pause the video here, compute your integral, and turn it back on to see if your work matches mine. Hopefully you also got the result that the volume of that space is 8/15. Let's take another look at it in our picture and see what it looks like as we increase the number of boxes going towards infinity. We're now up to 47, 78 boxes. Do you see that shape starting to develop? The maximum number of boxes of the applet is 100, but you can see that this is really an interesting shape. This is similar to one of the ones that I showed you at the very beginning of this video, where the cross sections are squares, but the base shape is parabolic. Now let's take a look at our next example, which is example number 2. In example number 2, let R be the region in quadrant 1 bounded by the curves y equal x cubed and y equal x squared. Suppose a solid has a bottom that is this region, and the cross sections, which are perpendicular to the xy plane, are parallel to the y-axis and are semicircles. In other words, our base is the area between x cubed and x squared, and our cross sections rising up off the xy plane are parallel to the y-axis and they're semicircles. Find the volume of the solid. It's a little hard to imagine what this one looks like. It's almost sort of like having, well, I guess you've got semicircular tube running along this sort of crescent shape that we have right here. Let's take a look at the applet and see if we can enter this in. Notice that the two curves, x squared and x cubed, intersect in two places in quadrant 1. They intersect at the origin, which technically is not in quadrant 1, it's on a boundary, but they also intersect at the point 1, 1. So since these intersect at 1, 1, we know that the x values are going from x equals 0 to x equals 1. Since we're slicing parallel to the y-axis, that means we're slicing this way, which means that our differential will again be dx. If we slice parallel to the x-axis, then the differential would be dy. We want to find the volume of this solid. Here's sort of an image of what it looks like. And here is one particular semicircle that we have. Notice that the distance between the two curves provides the diameter of the semicircle, and the radius is half of that distance. That means that the radius is going to be half of f of x minus g of x. Since x squared is above x cubed when we're going from x equals 0 to x equals 1, we have 1/2 of x squared minus x cubed. The formula for the cross section has to be the formula for a semicircle. The formula for the area of a circle is pi r squared, so the formula for the area of the semicircle is half of pi r squared. That will give us the formula that the area of the cross section, 1/2 pi r squared, where r is half of f of x minus g of x. If you work out the algebra, you should come up with 1/8 pi times the quantity x to the 6th minus 2x to the 5th plus x to the 4th. Pause the video and confirm that that is the correct formula for the area of the cross-section. Now let's take a look at putting this into the Geogebra Applet. Remember that our upper region is x squared and our lower region is x cubed. We want our cross-sections to be semicircles. So we're going to click on semicircles with the diameter in the base, and we're going to say that we want x squared for the top. That means that I also need to have x cubed for the bottom. So I enter x to the power of 3. We also want to go from 0 to 1, and let's put on a smaller number of boxes. 100 seems a little bit of overkill. Let's put on 6 boxes again so that we can see what it looks like. Now I will warn you that the applet has trouble drawing what these look like for semicircles. The best it can do is a single semicircle, but it doesn't give you the full effect. That is not actually what it would look like. Let me show you in the webcam what it would actually look like. As I said, this applet has trouble with this cross-section shape. It does a good job with the rest of them, but the semicircle seems to defeat it. All it does is show you one of the bases, but that's not what the cylinder looks like. This is what the cylinder looks like. Notice that it definitely has a height between the two sizes that are the same size, same shape, both semicircles, and parallel to each other. This distance right here, that is the height of the cylinder, and it's also our differential dx. So this is what each of those shapes should be looking like. It's just having trouble drawing them. Let's go back to the screen and complete this example. Let's increase the number of circles so that we can start to see the shape developing. As we go across, you can see that they're starting to get larger and larger. We'll blow it up a little bit. Unfortunately, if we blow it up too much, we sort of lose the shape. But this is, again, that crescent shape between x squared and x cubed. And this is sort of what it looks like. It's like, I don't know, it's sort of like having a Quonset hut or one of those isolation tent things set up over this along a long tube, and you're walking down the middle of it. So as you increase the number of slices, you increase the shape so that you can see a little bit better what it's starting to look like. Where each of the tops, of course, is this semicircle that we see there. This, of course, is the first one. Now, as we look at this, we need to set up or think about setting up our definite integral. The cross-section is a semicircle, and we have the formula for the area, and we also know it's going from x equals 0 to x equals 1. We're now ready to go ahead and set up our definite integral. Our definite integral then is going to go from x equals 0 until x equals 1. Writing x equal is not necessary, but I do want to emphasize that slicing parallel to the y-axis means the differential is dx, so the limits of integration must be x values. Our integrand becomes the area function of the cross-section, in this case the semicircle, which we saw was 1/8 pi times x to the 6th minus 2x to the 5th plus x to the 4th times the distance between the two bases, the two semicircles that we saw a minute ago in the webcam. And that's the differential, which is dx. Now go ahead and pause the video, compute your integration, and turn the video back on to compare your answer to mine. Hopefully you have that you can pull out the pi divided by 8 since it's a constant. That leaves you x to the 6th minus 2x to the 5th plus x to the 4th to integrate, which gives you this value here to be evaluated between 0 and 1. The 0 will, of course, make them all 0, so you can ignore that and focus on the 1s. That gives you 1/7 minus 1/3 plus 1/5, all multiplied by pi over 8. They are all prime denominators, so the lowest common multiple is 105. When you work it out, you end up with 8 times 105, which gives you 840, and the result is pi. Now, this is the end of this particular problem, but remember what you have found. This is an expression for the volume. So make sure that you understand that what you're computing when you do all of this is in fact the volume of this particular shape. I will warn you that most students find these solids where the region of the base is between two curves and the cross sections are different sizes and different shapes. They find this to be the most difficult material in both sections 2.2 and 2.3. In fact, to be honest, this is just about the hardest material in Chapter 2 altogether. The only thing that some students find a little bit more difficult is work, though I think most students would argue that work problems are easier still than this particular topic here. You will want to spend some time on determining the volumes of solids by slicing in order to make sure that you can master this technique. In the next video, we'll be taking a look at volumes of revolution by disks and washers. This will complete the material from section 2.2, and then we'll be looking at volumes of revolution by shelves, which is covered in section 2.3.